in this video, we're going to go ahead and talk about first and second derivatives and how they relate to the function. So questions 1 through 6 are referring to this graph here, and that graph is actually the derivative. It is the first derivative. So it makes a difference noting what graph we have, because how we interpret 1 through 6, it's all going to be in relation to the first derivative. So my first two questions have to do with f of x. I don't know what f of x looks like, but what I do know is that the first derivative is always positive, and if the first derivative is always positive, that means that the function f is going to be increasing over that interval. So wherever I start at x sub 1, I'm going to continue to increase, which would make x sub 6 the greatest value. So we don't care whether or not the first derivative is decreasing and increasing. That's referring to the second derivative and has other implications. What we're noting here is that the first derivative is increasing. The first derivative is positive, which means that f is increasing. So now questions 3 and 4 is related to the first derivative. Well, we're given the graph for the first derivative. So where it says, hey, where is the first derivative the greatest? It is the highest point on the interval, which maybe you could argue is maybe at these endpoints, but we're having to choose some of these x values down here. So the greatest value of the first derivative, given the x values that are selected for us, it's going to be at x sub 3. That's going to be the greatest one. So x sub 3. Where is it the smallest? Where is it the least? That's going to be at x sub 2, right? That is going to be the lowest point, x sub 2. So now let's go ahead and interpret the second derivative. The second derivative is going to be the slope of the first derivative. So the way that I interpret the second derivative is looking at all of these tangent lines on the curve. So where is the second derivative the greatest? That's going to be at the x value that has the steepest positive slope. So for example, at x sub 4, that is the steepest negative slope. I guess maybe you could argue that maybe this is even steeper. Yeah, I think that one's, ooh, that's a pretty good toss up. So I'm going to go ahead and say for this, the least one, I'm going to say it's either x sub 1 or x sub 4. But for the greatest second derivative, it's going to be the slope. Like this has a slope of 0. This has a slope of 0. But these each have, oh, here's another slope at 0. This has a positive slope. So x sub 6 is the only point there that's given to us that has a positive slope. I mean, we're positive here as well, but again, there's no like x sub 7, right? So it's only based off the x values that are chosen for us. Okay, so at one of the labeled points on the graph below, we want to know where the first derivative and the second derivative are positive. So the first derivative is going to be positive anywhere I'm increasing at f. So here's the interval where I'm increasing. That's where the first derivative is going to be positive. Where the second derivative is going to be positive is where you're concave up. So that's going to be along this portion of the graph here. So you can see it there overlaps b. So if I want to know where on the graph that I'm given, A, B, C, D, E, which one of those points has both a positive first and second derivative, that point would be B. The next set of questions ask us to interpret the first and the second derivative given f. So I have the option of choosing positive everywhere, 0 everywhere, or negative everywhere. So looking at number 8, because my graph is a constant, if I wanted to find the change of that constant would be 0. So both the first and the second derivatives are going to be 0 everywhere because there is no change. But number 9, there is a change. My function is decreasing, which means that my second derivative is going to be less than 0. It's going to be negative. But the derivative, because it's linear here, is going to be constant. So if we're talking about the second derivative, that's going to be 0 everywhere because that constant has no change. So 0 everywhere. Take a look at number 10. my function is increasing. So because my function is increasing, my first derivative is going to be positive. And because my function is concave up, we know that my second derivative is also going to be positive. Number 11, my function is decreasing, which means that my first derivative is going to be negative. But I'm concave up here, so my second derivative is going to be greater than 0. It's going to be positive. Number 12, my function is increasing, which means that my first derivative is going to be greater than 0. It's going to be positive. And because you are concave down, my second derivative is going to be less than 0. Finally, number 13, my function is decreasing, and my function is concave down, which means that my first derivative is going to be less than 0, and my second derivative is also going to be less than 0. Okay, moving along. Number 14, I'm given 4 different graphs, but all of these graphs represent the position of a particle. And so we're going to be asked a series of questions that relate to the velocity. So remember that the first derivative of position is velocity. So we're going to be interpreting the slopes of these position graphs. So where is my constant, where do I have a constant velocity? That's going to be here at graph 4, because I have a linear function whose change, right, or whose slope or whose derivative is always going to be constant. So 4. The greatest initial velocity. So again, velocity is the derivative of position. Derivative is just a fancy word for slope. So initially, graph 1 has a positive velocity that looks something like this. Graph 2's velocity is a little bit smaller. You can see that the slope changes. It's still positive, but it's not as steep. But look at number 3. Negative 3, or graph 3, draw that a little bit better. Graph 3's initial velocity is pretty steep. And then graph 4 has a negative velocity because that slope is negative. So the greatest initial velocity is going to occur in graph 3. What is the greatest average velocity? So we have to look across the entire interval. Average meaning from here to here, the average would be 0. From here to here, my average would be positive. From here to here, my average would also be positive. And from here to here, my velocity would be negative. So I'm looking for the greatest one, and 2 is just has a slightly steeper positive slope, so I'm going to go with number 2. But in part D, I'm asking for the 0 average velocity, which is graph 1, right? From endpoint to endpoint, that's a 0. And the next 2 questions ask about acceleration. So acceleration is going to be the second derivative of position. So we can interpret 0 acceleration, positive acceleration, negative acceleration, and so forth as the concavity. So for example, in my first graph, because I'm concave down, we would have a negative acceleration, but because I'm concave up, later that would change to a positive acceleration. So E is asking for 0 acceleration, which means that you're neither concave up or concave down. The only graph that is neither concave up or concave down is that line, so graph 4. And then a positive acceleration throughout means that even though like graph 1 has a portion of this interval that has that's concave up, which would be a positive acceleration, we want something that's going to be throughout the entire interval, and that's going to happen at graph 2. You are strictly concave up on that interval. It's not going to be graph 3 because you're concave down. Okay, Last but not least, number 15, I want to know, hey, given these two graphs, where are you not continuous? The only place that you're not continuous is going to be at F. You're not continuous at f of 1 because there is a jump discontinuity. But part B asks, hey, where are you not differentiable? So you're not differentiable also at f of 1 because you're not continuous. So because the graph is not continuous. And then in graph G, derivatives, even though you're continuous, will fail to exist at vertical tangents. Oops, let's see, erase tool. At vertical tangents, as well as these corners here because the slopes don't agree from the left and the right-hand side. So you're also not differentiable at G of 2 because there's a vertical tangent. And G of 4 because you have a cusp, meaning that the slopes from the left and right don't agree. The end.